Okay, here's another What the Physics video. This one is on, oh, it's a ranking activity. That one's especially cool. It's once again on torque. This is supposed to be an extended body at rest, although I'm going to put up a little bit of a fuss on there because the way that the textbook set it up, and as you can see, it's from page 238. The way that the textbook set it up, it's not necessarily at rest, but we're just pretending it is. So what we've got is we've got 5 different forces acting on this object here. And somehow the net torque is 0, even though they all have different, well, they could at least have different torques. So not, whatever. Okay, let's just pretend. Maybe that we can think of this instead of as a some type of a shelf with a hinge. Maybe we're looking at it from above and it's like a door. Okay, that would be okay with me. And because then I could cause the object to rotate, but standing as it is, if this is an above view of a door, it's not rotating. Still, it doesn't really belong in the in the um, in the extended bodies at rest section, but we're just talking about torque, so let's go. We're trying to figure out what the biggest torque is, what the smallest torque is, and so on. So a reminder, what heck torque is in the first place. Torque is equal to R cross F, or your textbook might use L cross F, same basic idea. And that means, well, what does that cross mean? It means R times F, that's the lever arm times the force, times the sine of the angle from the lever arm to the force. And that's why we do R cross F. It's got to be from the lever arm to the force, and it has to deal with, well, anyhow, that's good enough for right now. So we're going to put these in order using this basic equation. So making sure we have an idea of what we're talking about. This is force 1, this is force 2, this is force 3. They are all the same size, except they're pointing in 3 different directions. Force 5 is also the same size. They're all size T. And then force 4 is only half of that. And notice, of course, the distances will vary. So this distance here is half of L. This whole thing is the full F. So I'm going to use R as my equation, but let's go ahead and use L for the actual variables. So let's go ahead and solve these out. So let's see. Number 1, I'm going to do R cross F. So that would be, well, the L, and we'll use a capital L. L half times the force T times this angle right here. It's going to be sine of 60 degrees. So we plug that in and we get, I don't have any actual numbers for L and T, but that's okay. I'll just leave them in those terms. 0.433 L times T. And I'm going to have all these in terms of L times T. So that way we can still do a good comparison. 2 is still L divided by 2, then times T. And we're really just varying the angle here. Oh, this is 90 degrees. Sine of 90 is just going to be 1. So that's just going to be equal to 1/2 or 0.5 L times T. 3, once again, we've got L divided by 2 times T times sine of the angle. And this angle here, it's trying to be sneaky. It is, drop it down. It is trying to be sneaky because it wants us, no, it doesn't necessarily want us to do anything. It is daring us, perhaps, that's an exciting term, to use this angle here. We're not supposed to use that angle. We use this guy here. So the angle between the lever arm, R, and the force. You say, oh, well, what happens if the lever arm only goes out to here? Still, we would just extend it out to here and still use that. So anywho, that's going to be 30 degrees. So 30 degrees. Oh, I know that one off the top of my head. That's 1/2. So 1/2 times, okay, that's going to be 0.25 L times T. Number 4 is, oh, we're going all the way out here. Amazing. L times, well, except for now we're cutting the force in half. Outrageous. T divided by 2, and what's this angle business here? Well, this is 90 degrees. Sine of 90, once again, is 1. So 0.5 LT. Ooh, I see 2 that are the same value. Ooh! And then 5. Oh, I know this one. I don't even need to write it out, but I will because I'm awesome. L times T. So you might say, oh, this is going to be the biggest one, right? Well, yeah, so far until I say sine of 0. And I say sine of 0. What? That's 0. I can write out 0 times LT, but it won't make any difference. Okay? So where, if we were to rank these from the biggest to the smallest, let's extend. Well, let's see. These two guys are the same size, and they're the biggest. So let me rank these. I'll switch up the colors. T2 equals T, I'm sorry, I should say tau, not T. Tau 4, which is, both of which are greater than, well, let's see, the next biggest is tau 1, or torque 1, you can say. So I got that guy. And then, which is greater than tau 3, that was only 1/4 LT. And then, which is greater than tau 5, which was nothing. Nothing. So that's the order of the torques. Notice I was looking at it in terms of varying, well, in this case, mostly it was varying the direction. That was seemed to be the big guy. But it was also more in terms, it was also discussing in terms of force and the lever arm. So all three of those things are definitely going to be important. This could easily be expanded out to what if I had, so this is not part of the problem, but what if I had, you know, here, and it's the point of rotation is right there, and I had force, you know, here, and here, and here, but let's say the net torque on here, or I'm sorry, well, no, I can do that. Let's say the net torque on here is 0. Okay, so I'd say, oh, well, here's the center of mass, so that's a gravitational force right there. So how big would this force, force number 1, force number 2, force number 3, force number 4, and so on, have to be in order?
Anyone on the second and third floor, please use the rear step.
Well, that was distracting. How big would those forces have to be? Force 1, force 2, force 3, force 4. How big would, oh, let's I could do angles over here as well. Force 5, force 6. Can't really have this one because it's just not going to happen. I already know the net force, the net torque in there is 0. How big would those forces have to be to keep this, the net torque being equal to 0? That would be a little bit more exciting here. And that would be a little more appropriate to be having in this situation where we're saying that the net torque is equal to 0. But, you know, what the textbook gives. Still pretty darn delicious if you think about it. Physics.